So I'm really excited to talk to you today. This work has been done at Netflix over the last few years. I started out. I came to a conference at Axos 3 years ago to Paris that was hosted by Curteo and shared my work on ghost ads. I'm going to give a little bit of background on that, but just by the show of hands, who here knows what incrementality is? All right. Who here has heard of instrumental variables? Okay, a little fewer. All right, great. That's about what I expected. So what I'm going to do is give you a little bit of background of incrementality. First off, this work has been supported by a lot of people at Netflix, and I'm really grateful to their support. So again, this is not just my work. This is the collective work of a lot of people putting in a lot of time, effort, money to discover these things, and so that's been really great. So first off, why does incrementality matter? Who here thinks that incrementality does not matter? How dare you? Okay, incrementality matters. Let me just give you a couple examples. So when I first started doing research at Yahoo, this was a decade ago, we saw a lot of plots like this. So when we'd have technical sales managers, they would analyze some data and they would see ad exposure happening on, let's say, day 0, and they would see a huge spike in ad attributed or ad related activity for the website. So for example, they'd see the ad, they would go visit the website, and then over the following days, it would kind of fall off like this, and relative to a lower baseline leading up to it. And so you'd think, well, maybe ads are driving visits to the website. That's really great. But then what we did is we ran an experiment, and the black line shows a control group of people who were shown a placebo ad instead, or an ad that was not actually related to the advertiser. So somehow there was a huge spike of activity on the day the ads were being shown to people. And what was going on here? Was it that the ads that had nothing to do with the website were causing people to visit the website? No, it's just that people were online, and on day 0, people were seeing ads. People were visiting the websites. They were going shopping. They were reading the news. They're doing all the things that they do online. And the day before, maybe their cookie didn't exist on average, or maybe they were on vacation. That was just not the day that they were online. So we coined this a term called activity bias, which is just a way of describing selection bias that's related to contemporaneously correlated activities. So this is just yet another example of where correlation is not causation. So to just underscore this point, you think it's easy to measure the effects of advertising. You would just compare online purchases made by those who have and those who have not seen the ad, or at least that's according to the Harvard Business Review in 2008. This was one of the articles that came out during my first internship at Yahoo Research. And I was so surprised to see this, and so was my advisor at the time, that this quote is now going down in infamy. So it's really great to see that this is really not the case. And who here has seen this study by eBay, eBay search advertising? Almost nobody. Great. Okay, so I can show you that here on the left-hand side we have Google search results, where these are paid links that go to eBay, and down here we have unpaid links. Over here we have links to Macy's. These are paid ones, and these are the unpaid search results. So the question is I guess the question really comes down to, when you type in Macy's or eBay, where do you think you're trying to go? Trying to go somewhere else? No, you're trying to go to that place. So why would you need to have an ad here in order to encourage people to show up on your website, when all it does is compete against yourself? So the economists at eBay said, well, this seems kind of crazy. Why in the world should we be paying tens of millions of dollars for these types of ads every year? And there's some promotional reasons, like you can specify wedding registry in a different way than the organic links allow you to do. So I mean, there is some potential value here. But what they ended up discovering is that when they turned off these ads, so they turned them off at this point, what ended up happening is everybody just clicked on the other links. So the ads got shut off, and people just visited the other site. So in essence, the substitution was almost perfect. They did it both on MSN and they did it on Google as well, and they saw very similar results. These are log scales, I think, which is why it doesn't go all the way to 0. And they said, all right, well, that's just site visits. Well, maybe it had an effect on sales still. And in this case, they saw absolutely no effect on sales. Again, eBay is not representative of every advertiser out there, but they are an advertiser that was spending a large amount of money on these types of search ads. And so the real question was, how did they not know that their ads were not effective? And it really comes down to the point that they weren't experimenting. That when they turned off their ads, they didn't actually turn them off to learn the effects of the ads. They actually turned them off in order to compete with Microsoft in a bargaining situation. So Microsoft was threatening at this point to keep the reserve prices high, and eBay said, we don't want our reserve prices that high. We think you should lower them. So they were trying to negotiate, and so they shut off their ads, not for the sake of learning how effective their ads were, but as a bargaining position to try to get lower cost ads. So they figured out how to get lower cost ads by not buying them. So kind of an interesting thing. So in this case, what they found is that they could save more than $50 million a year by not buying these types of ads anymore. And instead, they figured out that they actually could make use of a consumer heterogeneity very much in the spirit of the things that the two speakers earlier today have spoken to about bandits and reinforcement learning. They figured that they could actually learn from this exploration in order to exploit the fact that for some people, the ads actually were effective. It just wasn't the lion's share of the people. So they were able to rejigger their strategy, and as a result, were able to be more effective, more profitable going forward. So let's define incrementality, just to be clear. Incrementality is about showing ads to some people. So let's say in the treatment group here, we show the ads, some people see the ads, and some of the people in our treatment group are not going to see the ads. Why don't they see ads? Maybe they're not eligible for them. Maybe they didn't show up online today, so we couldn't actually handcuff them to the computers and force them to type in go shopping online so that they would be able to see the ads. And then what we'd really like to do is compare it to the counterfactual. This control group of people who would have seen the ads, but instead of showing them the ad for Netflix, for Daredevil, we instead show them something else. So this ghost here is in reference to ghost ads, and that we want to record the counterfactual event, the counterfactual impression that we would have shown them an ad. So then we compare this green group to this green group so that we have a clean comparison. What typically had happened in the past is that the green group would be compared to the red group. But you can see that the composition of the green group shows a bunch of striped-shirted people, and has a different composition relative to the striped-shirted people down below. And so in this, if you compare apples to oranges, guess what? You're going to conflate this the correlation with causation, and you're going to get the answer wrong. Okay, so incrementality, it's the causal effect of an ad. So we're just doing causal inference. The advertising industry invented the word incrementality. I'm not responsible for it, so don't blame me. It's just the way to say we want the actual causal effect. We want the estimate that you would get from essentially a randomized experiment. So for example, we'd have a control group here where they would see other advertisers' ads, and they would perhaps generate $1 million of revenue. And then in the treatment group, we would see $1.1 million of revenue. And so the incrementality is the extra $100,000 that's generated by showing the advertiser's ad relative to what would have happened had we not shown that ad. Okay. Pretty clear, right? Seems really logical. So in this case, it allows us to establish per impression revenue gain. So in this case, it's $11 revenue per mil or per 1,000 impressions. And what we see is the average CPM is $3.40. So depending on the gross margin of this advertiser, so if their margins are about 30%, it turns out they break even. Okay, but the question really shouldn't be so much about do we advertise or not. It should be, exactly how do we price the advertising so that we can do it more optimally. How can we figure out how to spend it more efficiently? And so in this case, for this outdoor retailer, perhaps we can identify a group of outdoor enthusiasts. And so maybe the outdoor enthusiasts are responsible for $80,000 of that 100,000 gain, and the not outdoor enthusiasts, a group of people that we can identify beforehand as not being generally as interested in the outdoors, maybe they only generated $20,000 of this. So the great thing about this is just this one feature or this one characteristic allows us to compute upper bounds on what our willingness to bid should be. And so in this case, this group accounted for 4 million impressions. So we can establish a $6 CPM as the upper bound for this particular advertiser. So we're just doing some simple arithmetic here, but it's based on the fact that we have this $80,000 number and the 4 million impressions and the 30% gross margin that the advertiser has. And likewise over here, we can do the same calculation for the not outdoor enthusiast, and allows us to establish $1.20 as the threshold. So if it turns out that before we were bidding $3 over here and $3 over here, we were throwing away money on the not outdoor enthusiasts, and we were missing out on arbitrage opportunities for the people who are outdoor enthusiasts. So this just allows us to do exactly the same thing we've been doing with programmatic advertising, except instead of bidding against the total revenue count here, we're just bidding in a way that's consistent with the incremental revenue that's being generated, having subtracted off this baseline. Okay, any questions about that? All right, so that's incrementality in a nutshell. So how are we going to estimate it? We can do it using simple plots like that, but that really doesn't work in practice. So we need to get a stronger model to work around with this. Okay, so what we would do is we'd set up a directed acyclic graph, or maybe this is cyclic, in order to estimate this. And this is going to fit into the standard econometric frameworks that you might have heard of linear regression or more complex regression methodologies, if you like, and machine learning. And instrumental variables is the direction that we're going to go. So in particular, we're interested in the causal effect of ad exposure on purchases. We want to know how big of an effect there is, and sometimes we might not have full control over whether an ad is even shown. And so what ends up happening is that user attributes affect purchases, and if we're any good at marketing and our machine learning models are any good, it's going to turn out that these things that we can observe that our user attributes are going to cause ad exposure and purchases to be correlated. So in the case of Macy's or eBay, it's people are typing in eBay and are seeing ads because they're interested in buying stuff from eBay, and they're also buying stuff from eBay because they're interested in buying stuff from eBay. So you're sort of seeing ads, and it's a sort of a joint outcome because of these other attributes, which are you're intrinsically interested in visiting eBay. So some of these are going to be observable, and some of them are just going to be unobservable. So in the case of real-time bidding, for a company like Criteo, it could be that you're bidding into a marketplace with information that you have, but then let's say AdRoll or DoubleClick or some other bidder is coming in, and they have their own private information that they've acquired. And so the reason why you lose the auction isn't because of something that you observed, but because of something that you can't observe, that they are observing. And that, as a result, is causing them to sort of siphon off people differentially in a way that you don't have control over. And that's really what these unobservable user attributes are about. It's that you lose the auction for reasons that you cannot observe. And so the way to get around this is that we just experiment. We do the same thing we've always done in sort of reinforcement learning problems, is set up some randomization, set up a contextual bandit, and sometimes we're going to show ads, and sometimes we're going to not show ads. And by so doing, we're going to make sure that the outcome is only correlated through the ad exposure. And in some sense, we're bypassing the effects of W, not through uniform randomization necessarily, but through maybe conditional randomization in the way that John Langford spoke to earlier. So we just need to introduce some randomization, and we can solve this problem. And then we end up identifying the effects through this channel. So if the world were that easy, that would be really nice. It turns out it's not, because there's these things called positive and negative targeting. Essentially, what Criteo's business is built completely on top of is the ability to show ads to people and stop showing ads to other people in a way that's either correlated with them buying or not buying, or being interested or not interested in these ads. And the nice thing is that instrumental variables framework allows us to get this full cycle. So if it turns out that one ad causes you to buy something, and then buying something causes you to not see ads or to see more ads, that we will then estimate not the full cycle of the effect, but the partial contribution of each impression. So each ad will get its own share of credit, and that share of credit might be compounded by its effect even after another ad has been shown. Perhaps the first ad is shown and it has an effect 3 ads later, just due to the way the things work out. So the nice thing about all this is that because of this, we're able to fully resolve this problem. And so this is the type of framework we want to use in a real-time bidding situation where we have these unobservable confounders, or these omitted variables. All right, so what does this look like in sort of econometric notation? A simple incrementality model just says with the outcome, we can model it as a baseline plus the incremental effect in the number of ads. And then there's going to be a random error. And so delta y models the effect, the expectation of the outcome when we show the ad minus the expectation when we don't show the outcome, show the ad. And so we can't actually observe these both for a given individual, and so we're just using the model in order to construct this counterfactual. So we either showed you the ad or we didn't show you the ad, and we're going to use the model to construct the other expectation. Okay, so beta is the causal effect of the marginal effect of a single ad. And then what we'll do is enrich this model in kind of standard machine learning ways by just including a whole bunch of other features. And so in this case, it could be a whole bunch of interactions, or it could be that we allow this variable to be something like the number of ads shown to a person for a given country. And so then we can get heterogeneity, or break down the causal effect into its components, such as we have a couple of examples here. They could be outdoor enthusiasts, the number of impressions shown to an outdoor enthusiast, the number of impressions shown to people in the USA or France, or the number of different impressions of different ad sizes. So in the same way that you might break down the total value of a house into its number of bedrooms, bathrooms, maybe the plot of land, and maybe some of the other amenities that are included, how nice the kitchen is, you can break down the effect of an ad into its constituent components of its size and characteristics of the ad itself, and perhaps the person, maybe even some information about the history of the impression. Is it the 5th impression they've seen, or is it the 50th? Okay, and so in the end, we're going to have this incrementality, which is the delta y, delta yij, where I index is the person, j index is the impression. And so we want the total value of each impression so that we can give credit to each contributor. So each website needs to know how much value they generated so that we can know, do we still want to be able to buy ads on that website or not. Okay. All right. And so the way we do that would be nice if the world were that easy, but we're actually going to need to use an instrumental variables model to do this. And so in this case, we still have the same regression that we're trying to measure the causal effect of. We want this beta parameter, but we're going to have to set up another equation which says essentially the z value is going to be, did we try to bid on them versus not? And then the outcome here is the number of ads that were shown. And so this pi1 parameter is something like the win rate in the auction. So if we only win 10% of the ads that we bid on, then this will be a 0.1, and this will, say, be 10 ads, and we'll end up seeing that this is 10 bids, z, and then maybe they will only have one ad that they actually end up being shown. But the thing is, this is very standard framework in econometrics. It's been around for the last 50 years. In order to estimate supply and demand, we always had to disentangle prices, disentangle price and quantity scatter plots into both their supply component and their demand component in order to estimate these types of challenges. So in this case, what we have is a shifter that is the randomized bids, which are going to cause people to see ads in a way that's uncorrelated with other things. So, okay. So this is going to be our workhorse. And then we can just make a heterogeneous version of it that is just a really big regression. So it starts to look just like your standard click prediction problem that you would have in a typical bidding scenario, except in this case, we have this baseline nuisance parameters which say, what's the probability that you sign up for a Netflix subscription, say? What's the probability that you sign up even if we don't show you ads? And then this is the part that says, well, what's the contribution of the ads to your likelihood of signing up for Netflix? Okay, all right, any questions at this point? All right, so this is the setup of the problem. So I wish it were that easy. It's just not, okay? So when it comes time to talk about things, machine learning in the real world has a bunch of challenges in it. So for example, in a real-time bidding scenario, we're talking about over 10 billion auctions a day. I don't know, what's the number nowadays? Is like 50 billion that Criteo runs through? I forget. I read it recently. Over 1 billion users a month. I think we heard 1.8 billion earlier today. We have really cheap ad impressions, and when ad impressions are cheap, you should expect the actual causal effects of them to be very small as well, right? Like you just know it's like a needle in a haystack problem. But we have challenges with like continuous streams of data, where you don't have control over when people see ads, and so you have to have a model that's going to be able to account for the sort of continuous dynamic characteristics. So. I'm just going to focus on kind of these main three things. How do we deal with the huge scale of data in continuous time? And then how are we going to disentangle correlation from causation? We're going to use IV, but these instrumental variables, but we're going to have to be careful about how we go about it. All right? And so here's the solutions to each of these 10 problems. Again, focusing on downsampling, continuous time modeling, and what I'm calling the Hausman causal correction. And that'll make more sense later. OK. So how do we want to model incrementality in continuous time? So who here has heard of an ad stock model in the academic literature? OK, so not very many people. This is a sort of a cute way of modeling things that gets done in a lot of marketing and advertising research papers in the academic literature. So, but what does it really boil down to? It boils down to just saying, how many ads have you seen? And then you just sort of let them depreciate or decay over time. So if you saw 100 ads over the last month, maybe 20 of those, the equivalent of 20 of those last into the next month type idea, so that you have some sort of memory of it. So just to give you an example of how ad effects sort of decay over time, here's an example from a large sporting event. Those of you who might have heard of it, it's called the Super Bowl. It's not quite as popular as the World Cup, but at least around here, I think. But the important thing to note is that each one of these green spikes is the moment at which a television commercial was aired during the Super Bowl. And then the dots reflect a histogram of the number of searches that happened within, I think it's a 1 or maybe it's a 5-second interval. And so what you see is that it takes about 30 seconds from the start of the commercial for people to start visiting the website for there to be a spike. And you can see that there's definitely more searches after the ad than before, but it does tend to taper out over time. And then another thing to note is that there's no spike where there is no commercial, and so you don't have to worry about that activity bias thing I was talking about earlier. It's not just that there's a commercial break, so everybody's searching for everything online. It's that the ad is actually causing this effect. Okay, so another example here is in display advertising. At time 0, the ad was shown, and then after the ad was shown, this is the number of seconds following the ad exposure. These are searches for the retailer. Let's just call it Macy's. So these are the searches for Macy's. And so there's a big spike immediately following the ad exposure, and then it goes down. But in this case, it turns out that in online settings where you're just browsing, that there is a bit of a spurious correlation here. So this is searches for Craigslist after a Macy's ad. So here we got another activity bias problem, is that you see an ad, and then what's something you do within the next, say, like 20 to 30 seconds? You go and type something into the search bar, and you go somewhere else. That's just what people do. They navigate from one website to the next, and on some of those websites they see ads, and then sometimes they end up at some other website because they're just navigating around. All right. So, but is there a causal effect, and what's the shape of it? Well, in this case, you can see that there is we have a control group now. So this control group was shown this particular ad, and then this was shown retailer's ad like Macy's. And so what we see is that the spikes are in fact bigger closer to the time when the ad was shown, and then they tend to taper off as we get further out in time. So the type of shape that we're going to use to model the causal effects of ads is going to be something that's somewhat exponential-like. So we're going to have this baseline, which is modeled by this alpha term, alpha of t, in continuous time, and then we're going to have another feature that we're going to build, which looks like it's in continuous time, but it turns out we're just going to evaluate it at a particular moment in time when it comes time to train it. But this feature, in this case, we're just going to use an exponential kernel. You can use whatever kernel you want. It doesn't matter. You can just depends on exactly what shape you think it's going to be and how non-parametric or semi-parametric you want to be in the modeling. But the key thing to note here is that this is going to be the incrementality over time, is that the incrementality in this case is not a constant. As you sort of think about it over time, is that because the incrementality is much bigger at the beginning than it is as it sort of tapers off. And it turns out that this is going to help us a lot with the statistical power. So we're gonna get a lot of benefit from actually modeling the effect of the ad in a way that's that discounts it discounts the incrementality that doesn't exist far from when the ad was shown relative to when it was in close time proximity to it. Okay. So suppose you don't like that shape. Well, we can make a different shape. So we can add two kernels together, and guess what? They make this nice red shape. So all we need to do is just add more features to the model, and it'll do flexible things for you. And so this is just what we'd call semi-parametric statistics. So now suppose we showed another ad. Well, these ads are going to start stacking up on each other. So in this case, we're going to have two ads, one that's shown at this moment, another ad that then shows up at this moment. They're in different colors just so you can see that there's two different ads and that they may have a different shapes. They may be built because they have different characteristics. Maybe they're on different parts of the website, so maybe some of them are further down the page, and so they take a little bit longer for those ones to be noticed than the ones that are at the top of the page. And what you would like is the model to take care of all of those variables for you under the hood. You'd like it to understand the characteristics of the ad, just like you would if it was a house that you were trying to figure out how much it's worth. It would add up all those things together. So here's then we could add a third ad, and it has a different shape. They all have different shapes and sizes, and maybe even they have different decay patterns, as I was saying, depending on where they're on the page. Okay, so but in the end, we don't get to observe this beautiful plot. We get to observe this histogram, right? We get to observe when conversions happened over time. We don't get to observe which ad caused which conversion or not. And so this is where we're actually going to need to build the model in order to do that. So really what we want to be able to do is break it down into its baseline and its incrementality. And that's what we'll be able to do if we have a model. So we'll be able to estimate this baseline, and then we'll estimate the incremental part, which in this case, for this conversion that happened at this moment in time, this one conversion, we can attribute 70% of that conversion to being incrementally caused by the ads collectively, and 30% on average, it was going to happen anyway. So even though we can't take a given conversion itself and say this one was incremental versus was not, because we just don't get to observe that in the real world. We don't get to observe that information. We can model what share do we think was probabilistically caused by it. So this is where having the model is going to allow us to then construct bids. So how much should we bid on each one of these ads? Well, it turns out that it's just the integral or the amount of area of each one of these curves. So if we've used exponential functions as our basis functions, what do they integrate to? Well, they all integrate to 1. And so the beauty is that our bidding function ends up being just some of these regression coefficients. So we can do that simple inner product that we have to do in 20 milliseconds or less very easily with a high-dimensional model, because we actually did all the attribution in our feature generation, and we're not doing some online time integral to figure out how much we should bid on this particular ad, because that's already embedded in all of our features. So that's a really nice characteristics of this design. This W thing here, that's just like if you wanted to weight different ads differently, like if you thought somebody was more likely to be a bot or not, or you had a viewability score that you wanted to incorporate as well, you could include it there. All right. So then, suppose we wanted to do some more attribution. We need to break down the incrementality share into its components for each of the ads. In this case, the first ad gets 39% of the credit, and the second ad is going to get 31%. And because the third ad happens after the conversion, naturally, it's going to get 0%. And you can see that very clear here is through the illustration. All right. Is there any questions about this plot? don't be shy. I'm gonna show you more of these plots. So, okay, all right. So another great thing is that because it's all additive, the way that the model is built, it turns out you can, if there's another conversion that happens later, then you can just sort of add up all the shares. And so in this case, 34% of this conversion was attributed to the third add, 5% to the second add, and 6% to the first add. And then 55% of it would have, we predict would have happened anyway. So this allows us to break down each one of the conversions into its contributions by each impression, as well as break each impression into its total contribution over all conversions. And this is exactly what you would need in an accounting system that would accompany any sort of bidding algorithm that you would want to keep track of causality of ad effectiveness. And this sort of last equation here shows the equivalency between that the incrementality summed up over all conversions of a user is the same as the incrementality summed up over all adds and conversions, so each one of these little numbers, as well as the incrementality over all impressions that a user sees. So in some sense, there's a nice accounting identity here. All right, so what does this look like over time? So suppose you were building a dashboard. You could have these types of numbers being tallied and added up over time. And as time goes on, you will have realized the value that an ad impression is giving you. So at the very beginning, what you'll see is the ad is shown, and we haven't seen anything, but after a time, we then see a conversion, and then we'll see another conversion. And so what you'll see is that the observed incrementality goes from 0 at the very, very beginning to those positive numbers, and the residual incrementality goes from the bid down to 0 after we have fully amortized the value of the impression. So this is kind of like, you're paying your rent at the very beginning of the month. You paid your rent at the beginning. You have 30 days of time that you get credit for, and as you go through the month, you live in it each day, or you don't. You either get the value from being there or not, and in that process, you can do your accounting. So, and if you still have 15 days left, you still have 15 days left. And so any sort of incrementality-based dashboard naturally should be doing something like this time integral and keeping track of the fact that the ads that you bid on stuff where you expect to see something happening in the future that hasn't happened yet, and so you should be accounting for that. Like one of the things that always comes up in any incrementality test or any experiment that people will run is that you'll start the test and the metric will say that the ROI is 0, or rather minus 100% on day 0 on day 1, and that's not true, because there's still some expected incrementality. It just hasn't happened yet. And so if you want to keep your clients happy, you need to make sure that you're actually forecasting what you expect to happen in the future in conjunction with what you've observed to have happened so far through the campaign. All right. So that's just sort of a practical consideration to keep in mind. So how are we going to estimate this incrementality in continuous time? Well, who here has ever worked with hourly data or daily data in their analyses? Okay, so who here has ever worked with data at the time of like a femtosecond or like a millisecond or microsecond or nanosecond? Okay, so all right, so you've probably been using events that were available at that time scale, but you were not building a data set that had every single person in it at every single millisecond and keeping track of that over time, because that would just be dumb, right? Yeah, so it would be dumb. But the thing is the way we build these types of models in econometrics is we would normally work with something like the big blocky data that you see right at the beginning, which is at the hourly level. But it turns out that that works just fine when you have humans making decisions where they get information today and then they make a decision about what's going to happen tomorrow. But when you're in a reinforcement learning problem where you have real-time bidding decisions being made with let's say 100 millisecond latencies or less, for example, you would want your bidder to be able to potentially condition on whether the other impression on the page, whether you won or lost that impression. So we're talking about lags of 100 milliseconds for feedback to enter the problem. And so why is this a problem? Well, I'll show you an example. But the key factor here is that we really we're going to need millisecond level sort of data in order to deal with this potential feedback loop that'll be introduced, but that will be computationally infeasible. So what we're going to do is use this continuous time model, and that's going to allow us to do that. And we're going to use some clever sampling to deal with it. And there's this, I think the most important observation you can have is that the variance of our estimates of incrementality are actually going to be proportional to 1 plus 1 over the share of negatives to positives. So suppose, who here likes to do equal positives and negatives? You know, you have like half of your data set for a classification problem is positives and half is negatives. Well, it turns out that you're leaving about, according to this formula, you're leaving about 50% of the variance reduction on the table by taking that approach. Because you could actually go and grab even more negatives, and you could just downweight them, and you would still have the same expectation, but you would reduce the variance of your estimates. And so in this case, we don't want to have an even balanced positive negatives, because we actually need a calibrated score, because we're trying to get prices, we're trying to get value. And so what we end up needing to do is we need something that's representative of the whole thing. So, but a rule of thumb here is that if you have 10 times as many negatives as positives, you'll be within 10% of the variance from using an infinite number of negatives. So it turns out we don't actually need every person at every millisecond in order to, and we just need to have them at the moments when something interesting happens, and then a representative sample of when nothing's happening that's interesting, just so that we know what the background distribution is. So in order to solve this problem, we came up with this method, which I call double negatives, but it basically just boils down to doing the same thing you normally would do with negatives, positives, and then because you're in continuous time, you need this extra thing to account for double counting of when you sampled the positives with the negatives. So this graph is just to show you that it in fact matters. The red line is what you get if it turns out that you just did the naive thing that we would do in machine learning, which is just take your negatives, take your positives, and squish them together. It turns out that if you don't have sparse data, and sparse is actually just with respect to the time measure, it's not actually, it has nothing to do with whether they're infrequent or not frequent. It depends on what you used as your time scale. Like if it's a daily time scale, then that can kind of mess with things. But it turns out that you actually perfectly fit this black line to the curve, which is what we want to do. So the double negatives kind of fix this problem. And so when does this actually happen? Well, what we see in the top here is that we're going to have a case where suppose we did our sampling time as like hourly ETLs, or hourly data snapshots, and up here this person is going to see 2 impressions, and they're going to have 1 conversion, and the person down here is going to have 3 impressions and 0 conversions. And why don't they get to see the third ad? Because we negatively targeted them. They signed up at this moment in time. We turned off the ads, and then as a result, we stopped showing them. So what we get here is a correlation of -1. And essentially, that says that ads cause you to stop buying. So if you don't take care of this type of problem in a real-time bidding setting where you have this high frequency or high temporal frequency of feedback, you're going to end up in an environment where you potentially are going to underestimate the effects of the ads. So something to just keep in mind. And it turns out that this isn't a whole lot harder than just building the model. There's nothing fancy here. It just had to do with how we did the sampling. So this just shows that it actually works. So here are the true parameters of these. So this is the incrementality is, say, a $1.32. And over here, we see that as we increase the temporal granularity all the way down, it goes down to, it actually gets close to the right answer. And this is just a simulated example. So, but it's kind of nice to see that the biases can be really bad, but then it can also sort of clean itself up once you've reduced it. I think did something weird in the order there, but okay. So what happens, what is endogeneity? Endogeneity is this activity bias thing, or it's when another advertiser buys the ad for reasons that you can't keep track of. And so, but this crops up all the time. So in this case, it would be great if it turned out that ads just had an effect, and we could observe the pre-period, and then we could just extrapolate the pre-period into the post-period and observe what the shape looks like. But it's never like that. What ends up happening is people visit RottenTomatoes.com and looking up, let's say, House of Cards for Netflix, and what we end up seeing is that people sign up for Netflix after visiting RottenTomatoes.com, and we showed an ad on RottenTomatoes.com. So then the question is, well, was it the website that caused them to sign up for Netflix, or was it the ad? And if we're always showing the ad on the website, we can't disentangle that. Or if we're always showing the ad to particular people on that website, we can't disentangle that. And I wish it were that bad, but it's usually even worse. It's usually more like this, like they're doing things that are kind of related to Netflix before, and so they're likely to sign up, and then they go and visit Rotten Tomatoes, and before you know it, they've actually seen 3 ads and visited 3 websites, and it looks like a complete mess. And so I just say that it's infeasible for you to imagine that you could actually model this baseline all perfectly. So it turns out that you can actually get rescued from this problem by using randomized experiments, and you don't even need to estimate this baseline properly anymore. You can kind of punt on it. You can call it an omitted variable, but it's one that's going to be uncorrelated with your ad buying. And so you do this with randomized ad buying. If it turned out that every time we won or lost an auction, it was just due to randomness, meaning no other advertisers out there had any information that we didn't, and we also didn't really, we didn't mess around with our algorithms in exploration ways that were kind of, complicated, then this would be the way the world would work. It would be very easy. We could just win some ads, lose some ads, and we would know what the causal effect is. But it never is this way. So this is called strong ignorability or unconfoundedness, and this is just not the case in real-time bidding. So what ends up happening is this type of thing happens, is the people we win are very different from the people we lose. See how the baseline moves up and down? And then, so the kind of the solution to this problem is if we could observe which ads we would win. So suppose we actually own the ad exchange, or we could simulate an ad exchange, then we can deal with this problem very easily. And so the ghost ads is really about solving the problem in this way. In real-time bidding, you actually have to solve it this way, which is you try to win, and sometimes you're going to win, sometimes you're going to lose, and then you're going to base all of your modeling off of this exercise of estimating instrumental variables, where you know that you're not always winning, but you still estimate the right size of the curve on average, and you're able to scale it back up in kind of in an IPS type way. Is sort of what it implicitly does. It scales it back up to the full size of the shape when you do win the ads. Okay, so that's really great. So we can solve that problem, and it in fact works. You look at this plot, and so one thing you should know about instrumental variables is it's always going to have worse out-of-sample performance in terms of predictive power than least squares. So you should not be looking at its predictive performance to evaluate it. So for example, which of these 2 lines do you think fits the data overall best? The red dotted line, that one, or the black dotted line? Who likes black? Who likes red? Okay, you're all wrong, okay? It's not red. We don't want red here, and let me show you why. So I'm going to switch the histogram so that the incrementality is on the bottom and the baseline's on the top. Remember, we don't care about the baseline. We don't even need it right, because that's not what we're going to use in our bids. We're only using the incrementality part. So it turns out that the black curve is actually perfectly estimating the incrementality in a way that we can then use for bidding. And it turns out that the red curve is just getting distracted by the convolution of the bias that's in there. That sometimes when we win, it ends up being higher versus lower. Okay, so where are we going with all this? So we want production-ready causal machine learning, and so I'm going to conclude with just one slide about the causal part. So there's this concept called the Hausman causal correction, so the Hausman test. So the Hausman test in econometrics allows us to say, should we believe in instrumental variables, or are we okay just going along with the correlational model of ordinary least squares? And so you fit in your favorite correlational machine learning and favorite causal method here. It's the same principle. So the nice thing about this Hausman test is it looks a lot like L2 penalization. So it turns out that we can construct a causal objective function here and do a form of L2 penalization, and it'll actually do this really nice convexification of correlation and causation for us, where if there's enough evidence to say that correlation is not causation, it'll give us back causation. And if it turns out that the evidence is not that strong, then it'll go the other way. It'll just allow you to disregard the noisy causal model. All right, so we've already seen this for the methods, so I will just conclude it works. And just a way to think about where all this fits together is that in machine learning, we're generally trying to convexify the space between correlational modeling that ends up sort of finding this optimal predictive point between a degenerate model and an overfit model. Regularized bandits, where we would use some form of machine learning to take some bandit or contextual bandit or reinforcement learning-based data. We might have a degenerate model for the reward function, or we could have sort of the best causal model we could get out of that. But really what we're looking for is something that brings the best of both worlds, because this ends up being really noisy. So the Hausman test is a frequentist test that allows us to say, do we want correlation or causation? And in the end, what we really want is something in the middle. We want this bias variance trade-off, and we want to get this optimal sort of Hausman causal corrected model, which says when there's enough information about causality to say that correlation is not causation, we will then have de-biased predictions. And when it turns out that our experimentation and our randomization says, well, hey, guess what? It's not really as bad as you worried, then you'll just get to use much more precise predictions anyway. So in the end, that's all I had to share. So thanks a lot for your time, and thank you.
So any question for Randall? So I do have a small question about your very end when you're speaking about ghost ad. Mm-hmm. So what would you do if you were in a setting where you don't have ads, for instance, if you're on Google Shopping, where you cannot just display a ghost,
right?
A ghost, well, I don't know what it's called, the ghost shops.
Yeah. So what would you do in that setting is the question. Yeah. So if there's an API, then you might be able to do some sort of geo experiment or some sort of stratified experiment where you sometimes turn them on and turn them off. But you will always need to be able to link the people that you are trying to show the ad to the outcomes. And so that's where, if it turns out you can turn it off on a particular set of keywords, and then you can track people based off of the keywords that they originated from. Like I know that some of that technology has been removed in recent years, depending on whether it's organic versus sponsored. But yeah.
Okay. Any other comments, question? Yep. Maybe.
So I have a question about, which I think is more related to ghost ads. Mm-hmm. So you gave the example of Macy's at the start, where sure. If you didn't display the Macy's ad, people would still go to that place. So mm-hmm. you could check that by using a ghost ad. Right. But isn't it also possible that if a competitor would get that place, that it would be a different reaction than for a ghost ad?
Sure. So I guess the question is, what are you trying to measure? So in most cases, a business cares about what would happen if they choose not to advertise. And if competitors buy up that spot, that's actually measuring the sum total of the ad effect and the competitive effect, sort of the business stealing effect. And that's actually exactly the effect that we want to measure. So if you're an academic and you want to know what the causal effect of an ad is in isolation, then that's what you measure. And but if you're a business, you care about the sum total of all effects of not showing the ad versus showing it. Yeah.
Last one.
Thank you. Yeah, so it seems that the instrumental variables that you are using are actually interventions on the bid, yes. Kind of randomization of the bids. And if we look back at the talks from this morning, it looks like we should be able to use the inverse propensity scoring estimators for directly using this randomized bids. So is there any, I don't know, qualitative difference? Or
Yeah. So the key distinction is exactly on this slide. It's non-random, non-compliant. So inverse propensity score modeling only works if it turns out that baseline's not moving up and down. So in other words, if when you try to show the ad, you always succeed at showing the ad, and when you try to not show the ad, you always succeed at not showing the ad. Somebody else doesn't come in and win the auction out from under you. You could potentially do this from a bidding perspective, where you say, I tried to bid, and then what's the return? The challenge is that you then have to go and estimate what's the expected cost. So you basically have to know what your expected win rate is, so that then you can scale your bid up and down, or you can just estimate directly what the causal effect is of the ad. And so they're sort of like two sides of the same coin, and in the end, you have to estimate all of the same things anyway. It just depends on whether you think that it's easier to estimate the bid, sort of what would be called an intent to treat type bidding model, or versus the actual structural causal model that says, here's when ads happened, and then there's the effects of those ads. But yeah, I think it's something to look into.
Well, then I think we can thank again Randall.
Thank you.